Welcome to another lecture of the course Mathematical Aspects of Biomedical Electronic System Design. We will continue with our study of linear algebra. In particular, in this lecture, we will look at row and column spaces, rank, null space, determinant, and trace. So let us begin the lecture. In the previous lecture, we learned about span of a collection of vectors. We will use that definition to define column and row spaces. So start with column space and row space. Given a matrix A, say it's a real valued M cross N matrix, we define column space of A to be the span of columns of A. Span of columns of A. Similarly, we define row space of A to be the span of rows of A. What we mean that if A is an M cross N matrix, say it has M rows and N columns, then each of its columns is a vector in Rn. So this belongs to Rn, and there are a vector in Rn, and there are n such vectors. Right? So there are n such vectors. The span of all these n vectors is called column space of A. Similarly, if you look at each of the rows, they are vectors in Rn. Vectors in Rn, and there are m such rows. The span of m rows of A is called row space of A. Clearly, each column being a vector in Rm, the column space is a subspace of Rm. Column space is a subspace in Rm. Similarly, row space is a subspace of Rn. Okay. Moreover, rows of A are columns of A transpose and columns of A are rows of A transpose. So, column space of A is same as row space of A transpose. Similarly, row space of A is column space of A transpose. Let us see an example. Let us consider A equals to a 2 by 3 matrix, which is equal to 1 0 3 0 0 1. In this case, each of the columns of A is an element of R2. So column space of A is span of the three columns, that is set of all linear combinations of these three columns, and it can be seen that it is entire R2. So column space of A is alpha 1 1 0 plus alpha 2 times second column plus alpha 3 times third column, that is 3 1, where alpha 1, alpha 2, alpha 3 are real numbers, and as I said, it is entire R2. Similarly, each of the rows of A is an element of R3. So the row space of A is set of all linear combinations of the two rows of A. Alpha 1 1 0 3 plus alpha 2 0 0 1, where as before alpha 1 and alpha 2 are real numbers. It can be seen that it is a strict subset of R3. It's a subspace in R3. Okay. The next thing that we will see is what we call a rank of a matrix. Okay. So for a matrix A, say it's M cross N matrix, it's a fact that its number of its linearly independent rows is equal to number of linearly independent columns, and this number is called rank of A. Number of linearly independent rows equals number of linearly independent columns. This number is called rank of A. And it's often denoted as rank in bracket A. Okay. So clearly the rank of A is dimension of row space of A, which in turn is equal to dimension of column space of A. Dimension of row space of A, which in turn equals dimension of column space of A. Let's consider the same example that we had seen before, that is A equal to 1 0 3 0 0 1. This is 2 by 3 matrix. Here the number of linearly independent rows is 2. There are only 2 rows and the 2 are linearly independent, and it can be seen that the number of linearly independent columns is also 2. So rank of A is 2. Each number of linearly independent rows, which is 2. Okay. It's clear that for any M cross N matrix A, its rank is less than or equal to minimum of M comma N. Clearly, the rank of A cannot exceed either M or N. For A, M cross N, a rank of A is less than or equal to minimum of M comma N. For instance, in the above example, we know that rank of A cannot be larger than minimum of 2 and 3, which is 2. Okay. If rank of A is equal to minimum of M comma N, then A is called a full rank matrix. A is equal to minimum of M comma N, A is called full rank. So A in the above example is full rank. However, if we consider another matrix, say B, which is a 3 by 3 matrix, 1 0 3 0 0 1 1 0 5, it can be seen that rank of B is 2, which is less than 3, so B is not full rank. Rank of B is 2 as it has only 2 linearly independent rows and 2 linearly independent columns. Rank of B is 2, B is not full rank. Okay, we will now state a few properties of rank. The first one is easy to see. It says that rank of A equals rank of A transpose. It is because the rows of A becomes column of A transpose and columns of A become rows of A transpose. Okay. Then the next property is a matrix A, square matrix A, is invertible if and only if its full rank. Only if it is full rank. For example, the matrix B in above example is not invertible. Not invertible. Another important fact about rank is if another important fact about rank is if A is a square matrix that is full rank and A B is equal to A, then B has to be an identity matrix. So let's see what it is. If A, which is say n cross n, is full rank and A times B equals A, then B has to be identity matrix. Okay, B can't be any other matrix. The next thing that we will see is what we call null space of a matrix. Null space. Okay. Given a M cross N matrix A, its null space is defined as follows. Null space of A, denoted as null of A, it is collection of all vectors in Rn such that A times x is equal to 0. So clearly it is a subset of Rn and it can be checked that it is a subspace of Rn. It is a subspace of Rn. Recall that to show that a subset of Rn is a subset of Rn, we need to show two properties. One is if x is in null of A and alpha is a real number, then alpha times x should be in null of A. Let's verify this property. X being in null of A means A times x is equal to 0, which further implies that alpha ax is equal to 0, and now using associativity we can see that A times alpha x is equal to 0, which says that alpha x is also in null of A. Okay. Similarly, we have to establish that if xy are in null of A, then x plus y will also be in null of A. Let's verify this property as well. The fact that x and y are in null of A implies that ax is equal to 0 and ay is equal to 0. This implies that ax plus y is also equal to 0, which in turn means that x plus y is in null of A. This way we have easily verified that null of A is indeed a subspace of Rn. Okay. The next thing is nullity. Nullity of matrix A is actually dimension of null of A. nullity of, so we are looking at nullity of A is dimension of null space of A. Okay, let's see an example. Again, let's consider 1 0 3 0 0 1. Null space of A would be defined as all vectors x in R3 such that Ax is equal to 0, which is x in R3 such that x1 1 0 plus x3 3 1 is equal to 0, which in turn means that null of A is equal to x in R3 such that x1 plus 3x3 is 0 and x3 is equal to 0, which in turn can be seen to be equal to collection of all vectors x in R3 such that x1 equals to x3 equals to 0. Clearly, nullity of A is dimension of null space of A, which in this case is 1. The next notion that we will see is range of A. For a matrix A, which is an m cross n matrix, its column space is often referred to as its range. So the range of A is nothing but column space of A. Okay. Clearly, if we are interested in range of A transpose, it would be row space of A. Okay. Now we will see a fundamental result in linear algebra. In fact, it's also known as fundamental theorem of linear algebra. It relates dimension of range of a matrix, its nullity and number of columns in A. So we will see what we call fundamental theorem of linear algebra. It says that for a matrix in R m cross n, dimension of range of A, which is same as dimension of column space of A, plus nullity of A equals n. Dimension of range of A is often referred to as, is also referred to as rank of A. So fundamental theorem of linear algebra says that rank of A plus nullity of A equals n. This result is also referred to as rank nullity theorem. As we see, it relates rank and nullity of matrices to their number of columns. Rank nullity theorem. Let's see a few examples. Let us take A to be the following matrix. It's 1, 2, 3, 2, 4, 6. Okay, it's a 2 by 3 matrix. It can be easily seen that rank of this matrix is 1 because the two rows are linearly dependent. If we multiply the first row by 2, we get the second row. Clearly the number of linearly independent rows is just 1, so rank of A is 1. Now we will investigate nullity of A. Towards that, let's write what is null of A. Null space of A, it is x in R3 such that Ax equals to 0. It can be easily checked that the vector 2 minus 1 0 is in null space of A. Why? We can verify that A times this vector equals 0 vector. Similarly, it can be checked that Similarly, it can also be checked that the vector 3 0 minus 1 is also in null space of A. Okay, so A times 3 0 minus 1 also equals 0. Further, the two vectors that we have written here are linearly independent. This says that null space of A, which contains at least these two vectors, has dimension at least 2. So what we see that nullity of A is at least 2. However, we will see that nullity of A cannot be 3. For nullity of A to be 3, all the vectors in R3 should be null space of A. We argue that, we claim that nullity of A cannot be 3. Why is this true? Because 1 1 1 is not in null space of A. It can be easily checked that A times 1 1 1 is not equal to 0. This says that nullity of A is indeed just 2. And now if we see both rank and nullity, we say that rank plus nullity of A equals 3, which is number of columns in A. Let's see another example, and this time we will consider the matrix A that we have considered earlier. So now we will consider A to be equal to 1 0 3 0 0 1. We have already seen that rank of this matrix, which is equal to dimension of column space of this matrix equals 2. We also saw that nullity of this matrix is 1. So rank of matrix plus nullity again equals 3, which is same as number of columns of A. Next we look at the notion of determinant of a matrix. Determinants are defined for a square matrices. Determinant of any square matrix is a real number. So for any square matrix A, say n by n matrix, its determinant is denoted as det of A. Its determinant is denoted as det of A, or sometimes as this. As I already indicated, det of A is a real number. Let's see how determinants are defined. When n is 1, that is, we are looking at 1 by 1 matrices. So let that is A is of the form A11, then determinant of A is just that number A11, just the element A11. When n is 2, that is, now we are focusing on 2 by 2 matrices. Let's say A is A11, A12, A21, A22. Then determinant of A is A11 times A22 minus A21 times A12. Let's see an example. Suppose A is 1, 2, 3, 4. Then determinant of A will be 1 times 4 minus 2 times 3, which will be minus 2. Now let us move to n equals to 3. Suppose A is matrix A11, A12, A13, A21, A22, A23, A31, A32, A33. Determinant of 3 by 3 matrices can be obtained via expansion along any of the rows or along any of the columns. Let's see what I mean. I'll first illustrate what I mean by expansion along first row. So I'll consider first row here for expansion. I'll take the first entry of the first row. I will now ignore the row and the column corresponding to that entry. That is, I'll ignore the first row and first column, and I'll write the determinant of the remaining submatrix. A22, A23, A32, A33. Okay. So one thing that I missed to say, that the whole thing should be multiplied by minus 1 raised to the sum of indices of the element that I started with, that's A11. So I'll put here 1 plus 1. Now I'll move to the next element of the first row, that is A12. So now I'll have minus 1 raised to, now the sum of the indices is 1 plus 2, A12. I'll again ignore the row and column corresponding to this entry, that is, I'll ignore the first row and the second column, and will consider the determinant of the remaining submatrix, which now becomes A21, A23, A31 and A33. Finally, I'll go to the third entry in this row, and I will now have 1 plus 3, A13 times determinant of the submatrix A21, A22, A31, A32. This is how determinant of matrix A, which is 3 by 3 matrix, can be written in terms of determinants of 2 by 2 submatrices. And here we have expanded along the first row. Right? We could expand along the first column as well. In that case, we will get the following expression: minus 1 raised to 1 plus 1. So now I am expanding along the first column. So minus 1 raised to 1 plus 1, A11. This entries will remain same, A32, A23, A32. This is A22, A23, A32, A33. Now I'll move to the next element of the first column, that is minus 1 raised to 2 plus 1 now, and this is A21. The submatrix that now I'll consider is A12, A13, A32, A33. Next, I'll go to the third entry of the first column. So I'll have minus 1 raised to 3 plus 1, A31. Now I'll ignore the first column and third row. So the submatrix that I'll have to consider is A12, A13, A22, A23. So this is how I'll write determinant of A using determinants of submatrices while expanding along the first column. I could expand along any row or any column and I'll get the same final answer. Let's see an example. So let us consider the 3 by 3 matrix 2 1 3 4 2 5 1 6 9. Let's compute determinant of A via expanding along the first row. So first minus 1 raised to 1 plus 1 times 2, and the submatrix that I'll consider is 2 5 6 9, then plus minus 1 raised to 1 plus 2, and now I have 1, and the submatrix that I'll consider is 4 5 1 9. Finally I'll consider the third element of the first row, minus 1 raised to 1 plus 3 times 3 times 4 2 1 6. Let us work out these submatrix calculations. So I'll get 2 times 9 into 2 minus 6 into 5, that gives minus 12, minus 9 into 4 minus 5, that gives 31. Then finally I have 3 times 6 into 4 24 minus 2, that is 22. So I have minus 24 minus 31 plus 66. On doing the arithmetic, I'll get final result 11. Instead, I could have expanded along the first column. Then determinant of A would be computed as minus 1 raised to 1 plus 1, 2, 2, 5, 6, 9. Then it will be minus 1 raised to 1 plus 2, 4 times. Now I'll ignore the first column and the second row, and here I'll have 1, 3, 6, 9. Finally, I'll have minus 1 raised to 1 plus 3 into 1 into 1, 3, 2, 5. It can be seen that I'll get the same final answer as before, that is 11. In fact, as I stated earlier, I could expand along any row or any column. So this is how we define determinants of 3 by 3 matrices. Now let's take this idea forward and consider n by n matrices. For A in Rn cross n, that is A has entries A, I, J, where I and J both are ranging from 1 to n. I can determine determinant of A by expanding along any of the rows or any of the columns. So let's say I'm expanding along jth column, then determinant of A could be written as I equals to 1 to n minus 1 raised to I plus j Aij, that is I'll move along column j, and here I'll have determinant of Aij, where Aij is the matrix submatrix of A obtained by deleting ith row and jth column. Okay, so I could expand along any column j. So for some j equals to 1 to n. Similarly, I could write determinant of A by expanding along say ith row, in which case I'll get j equals to 1 to n minus 1 raised to I plus j Aij. And now determinant of Aij, where again Aij is the submatrix that is obtained by deleting ith row and jth column. So I could do it by expanding along any of the rows. So let's see, let me write here where Aij is a submatrix of A. It has dimension n minus 1 cross n minus 1. This is submatrix of A obtained by deleting ith row and jth column. Okay, the above expressions that recursively give determinant of a matrix A in terms of determinants of its submatrices, they are called Laplace expansions. The above expressions are called Laplace expansions. Okay. The first expression is called expansion along jth column. Expansion along jth column. Whereas the second one is called expansion along ith row. Second one is called expansion along ith row. As we have already seen, Laplace expansions give a recursive method. Expansions and give a recursive method to get determinant of any n by n matrix in terms of determinants of 2 by 2 matrices. So how is it achieved? So you express determinant of n by n matrix in terms of determinants of its n minus 1 cross n minus 1 submatrices, which in turn could be expressed as determinants of certain n minus 2 cross n minus 2 matrices, and so on. If we continue, ultimately everything will reduce to determinants of 2 by 2 matrices as defined above. We will now see a few properties of determinants. Okay. The first property is for any matrix, for any square matrix, its determinant is non-zero if and only if the matrix is invertible. Is invertible. Let's take an example. Recall the following matrix that we had considered earlier also. It was 1 0 3 0 0 1 1 0 5. This matrix is not invertible. Is not invertible. It can be easily checked that its determinant is 0. In fact, in this case, it's trivial to check. If we expand along second column, we see that all the factors, all the terms in the expression of determinant will be 0. So determinant of A is 0. The second property is also a related one. We have already seen that a square matrix, a square n cross n matrix A is invertible if and only if its rank is n. We can combine this statement with the previous property to say that for a matrix A, which is n cross n matrix, determinant of A is non-zero if and only if rank of A is n. Okay, we will see now the third property, but before we see the third property we need a few definitions, and these are definitions of so-called upper triangular and lower triangular matrices. So let's see what these are. Lower triangular matrices. Let us consider a square matrix A. Say it's an n cross n matrix. The entries A11, A22, etc. up to ANN, these are called entries on the main diagonal. So this is called main diagonal of A. The matrix is called lower triangular if all the entries above the main diagonal are 0. So if all these entries are 0, then A is called lower triangular. More precisely, A, that is n cross n matrix, is called lower triangular if Aij is 0 for all I less than j. We can similarly define upper triangular matrices as before. Let us consider A, which is n by n, and this is its so-called main diagonal. If all the entries below the main diagonal are 0, then A is called upper triangular matrix. So A is called upper triangular if Aij is equal to 0 for all I greater than j. Now we are ready to state the property of determinants of lower and upper triangular matrices. This property says that if A is upper triangular or lower triangular, then its determinant is just the product of entries along the main diagonal. That is, if A is A, that is n cross n matrix, is lower triangular or upper triangular, then determinant of A is simply product of entries along the main diagonal. It is product of entries AII. Okay. Let's see an example. Let us consider the 4 by 4 matrix 1 1 0 1 0 3 4 0 0 0 minus 3 1 0 0 0 5. Clearly this is an upper triangular matrix, right? All entries below the main diagonal are 0. So determinant of A is, in this case, product of the diagonal entries, that is 1 into 3 into minus 3 into 5, which is minus 45. Okay. We now move to the next property of determinants, which says that determinant of A is same as determinants of its transpose. So this is number 4, which says that determinant of A is same as determinant of A transpose. Okay. Now we will see yet another property. It says that if A and B are square matrices of order n cross n, then determinant of A times B is product of determinants of A and B. So for A, B, which are both n cross n, determinant of A, B is determinant of A times determinant of B. Let's see the next property, but again before I state this property, I will give a couple of definitions. So the first one is so-called similar matrices. Similar matrices. Two matrices A and B that are both n cross n are called similar if there exists an invertible matrix S, that is again n cross n, such that B can be expressed as S inverse AS. Let's see an example to illustrate what I mean. Let's say that A is this matrix with 3 by 3 matrix with entries minus 13, minus 8, minus 4, 12, 17, 12, 7, 4, 24, 16, 7. And say S is 1, 1, 2, minus 2, minus 1, minus 3, 1, minus 2, 0. In this case, it can easily be checked that S is invertible and S inverse A times S is equal to minus 1, 0, 0, 0, 3, 0, 0, 0, minus 1. Okay. So let's say this matrix is B. So in this case A and B are similar. Similar matrices. Okay. We'll also see the notion of equivalent matrices. Two matrices A and B that are not necessarily square, so they are m by n matrices. They are called equivalent. Equivalent if there exists two other matrices that are invertible matrices R, which is n cross n, and S, which is m cross m, so that B is S inverse AR. Okay. Having defined these notions of equivalent and similar matrices, now we are ready to state the property that determinants hold for similar matrices. Actually, similar matrices have same determinants. Okay. So this is the next property. If A, B, both n cross n are similar, then determinant of A is same as determinant of B. For instance, if you look at the above example, where determinant of A is somewhat involved to calculate, but we can readily see that determinant of B, which is an diagonal matrix, is, and so it is both upper triangular and lower triangular. Determinant of B is product of its diagonal elements, so it is -1 into 3 into -1, which is 3. So determinant of A would also be 3 in the above example. Determinant of A is same as determinant of B because A and B are similar, and the latter is -1 into 3 into -1, which equals 3. Okay, now let's see yet another property, and this will be property number 7. It says that adding a multiple of a column to another column does not change determinant of the matrix. Similarly, adding a multiple of a row to another row does not change determinant of the matrix. Adding a multiple of a column or a row to another row or column, another column or a row does not change determinant of A. Does not change determinant of A. Let's see an illustration of this property. Example. So let's consider A equals to 5 minus 2 1 0 3 minus 1 2 0 7. It can be easily checked that determinant of A in this case is 1 0 3. Now if we multiply the last column by 2 and add the resulting vector to the first column, we get another matrix. Multiplying column 3 by 2 and adding to column 1, column 1, we get B equals to say 7 minus 2 1 minus 2 3 minus 1 16 0 7, and the previous property says that determinant of B would be same as determinant of A. Okay, let's see another property that says that swapping two rows or two columns of matrix A merely changes the sign of the determinant. The absolute value remains fixed. So swapping two rows or columns changes the sign of determinant of A, but the absolute value remains same. The absolute value remains same. For instance, if we swap the two columns of B, say first and second column of B, to get the following matrix C, then determinant of C would be minus of determinant of B, which let us recall was 103. So this will be minus 103. Okay. Finally, we will see one more property of determinants that says that multiplication of a column by a constant scales the determinant by the same constant. Similarly, multiplication of a row by a constant scales the determinant by the same constant. So it says that multiplication of a column or a row by say lambda, which is a real number, scales determinant of A by lambda. Okay, so what it means that if I define another matrix, let's see an example. If I define another 3 by 3 matrix D by multiplying the last column of C by 3, that is my D matrix is minus 2, 7, 1, 3, minus 2, 7, 3, 3, minus 2, minus 3, 0, 16, 21. Then determinant of D will be 3 times determinant of C, which will be minus 309. Okay. In particular, this property says that if I multiply all the entries of a matrix by a constant lambda, the determinant of the resulting matrix will be lambda raised to n times the original determinant. In particular, if I multiply all the entries of A by lambda, that is if B is lambda A, then determinant of B is lambda raised to n times determinant of A. Finally, we look at the notion of trace. Trace is also defined for a square matrices. It yields a real number for any square matrix. For A, which is an n cross n square matrix, its trace is defined as sum of all diagonal entries. So trace is denoted as TR A, and it's defined as I equals to 1 to n AII. Let's see a few properties of trace. The first one is an easy one. It says that for matrices A and B, both n cross n, trace of A plus B is trace of A plus trace of B. The second property says that if A is a square matrix and alpha is a real number, then trace of alpha times A is alpha times trace of A. This is again easy to verify. The third property says that for a matrix A which is m cross n and B which is n cross m, trace of AB, notice that AB here is an m cross m matrix, is same as trace of BA. BA clearly is n cross n. Okay. Let's see an illustration of this property. If we consider two vectors x and y, then xy transpose is a matrix, n cross n matrix. On the other hand, y transpose x is a real number, but the above property says that trace of xy transpose will be same as trace of y transpose x, which in fact will be y transpose x itself. Okay. The fourth property says that trace is invariant under cyclic permutation. Invariant under cyclic permutation. What does it mean? It means that if we consider K matrices A1, A2 dot 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 AK such that they can be multiplied, then trace of their multiplication will be trace of AK, A1, A2 dot 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 AK minus 1. Notice that here we have permuted the matrices in a cyclic order before multiplying them. Right, so the trace of the left hand side matrix is same as the trace of the right hand side matrix. Of course, here we are assuming that matrix multiplications are defined. Assuming that the matrix multiplications are defined. The next property is in regard to similar matrices. It says that similar matrices have same trace. So if A, B, both n cross n are similar, then trace of A will be same as trace of B. Okay. This was all about trace. Now I'll quickly introduce a notion that is of characteristic polynomial. Okay. For a square matrix A, let's say n cross n matrix, and a number lambda, determinant of A minus lambda I is a polynomial in lambda, and this is called characteristic polynomial of A, often denoted as follows: PA of lambda. So this is called characteristic polynomial of A. Notice that PA lambda is a polynomial of degree n. Okay. Moreover, if we write PA lambda as summation I equals to 0 to n Ci lambda raised to n, then Cn is minus 1 raised to n, Cn minus 1 is minus 1 raised to n minus 1 times trace of A, and C0 is determinant of A. These properties easily follow from definitions of determinants and trace. Further, for any matrix B, that is n cross n, we can define PA of B also as follows. So PA of B is C naught I plus I equals to 1 to n Ci B n. Then it turns out that PA of A is 0. This particular result is referred to as Cayley-Hamilton theorem. One of the uses of Cayley-Hamilton theorem is in finding the inverse of matrices. Suppose A is invertible, then from Cayley-Hamilton theorem, A inverse of PAA will be 0, which implies that C naught A inverse plus C1 I plus I equals to 1 to n Ci A raised to I minus 1. This is 0, and on rearranging terms we find that A inverse is equal to minus 1 over C naught C1I plus I equals to 1 to n Ci a raised to I minus 1. So we see that we can obtain inverse of a matrix A in terms of products of the same matrix. This brings us to the end of this lecture. Thank you.